Every physics textbook agrees on one thing. There is no equation that marks a difference between past, present, and future. Time appears in the mathematics of relativity as a dimension, not a flow, indistinguishable in kind from length, width, and height, except for a single minus sign buried deep in the geometry. This detail, easy to overlook, carries enormous consequences. It means the moment you are living through right now, according to the physics, holds no more reality than a moment 1,000 years ago or 1,000 years from now. The past has not gone anywhere. The future, in some sense, already is. This is the block universe hypothesis, a model in which all of time exists as a single unchanging structure laid out like a landscape rather than unfolding like a story. It is not a fringe idea dreamed up by philosophers with too much free time. It emerges directly from the mathematics of special and general relativity, tested and confirmed for more than a century through experiments involving atomic clocks, orbiting satellites, and particle accelerators. Physicists did not set out looking for a universe without flow. They arrived at one by taking seriously what the equations actually said, even when the conclusions ran against every intuition built into ordinary human experience. To take the block universe seriously is to confront a version of reality where movement through time may be nothing more than an impression generated by memory and consciousness, processing a structure that itself never changes. What follows traces how physicists arrived at this conclusion, beginning with a classical assumption so old it was rarely questioned through the experiments that broke it and into the strange geometric picture that replaced it. For over 200 years, one assumption sat at the foundation of physics so firmly that almost no one thought to examine it. Time in the world described by Isaac Newton was absolute. It flowed at the same rate everywhere in the universe, for every object and every observer, regardless of where they stood or how fast they moved. A second on Earth was a second on the moon. A second in a moving carriage was a second for a person standing still beside the road. Duration, in this picture, was a fixed background quantity, ticking forward uniformly, indifferent to everything happening within it. Newton described this idea explicitly in the opening pages of his Principia Mathematica, published in 1687, distinguishing what he called absolute, true, and mathematical time from the time measured by ordinary clocks and calendars, which he considered merely approximate, practical stand-ins for a deeper, unchanging temporal reality flowing independently of anything physical. This was not a minor technical assumption tucked away in a footnote. It was the scaffolding on which the entire structure of classical mechanics was built. Newton's laws of motion describe how objects accelerate under applied forces, and acceleration is defined in terms of how velocity changes over time. For these laws to produce consistent, reliable predictions, applicable equally to a falling apple, an orbiting planet, or a cannonball in flight, time itself needed to be treated as a stable universal reference against which all motion could be measured. If time ran differently for different observers, the clean mathematical relationships Newton had discovered would fall apart, producing different answers depending on who was doing the calculating. Absolute time provided the fixed stage on which the drama of absolute space could play out, with objects moving through a three-dimensional arena while a single universal clock ticked forward at the same rate for everyone, everywhere, without exception. It is worth appreciating just how intuitive this assumption felt, and still feels, to anyone encountering it without specialized training in modern physics. In daily experience, nothing about the world suggests that time might run differently for a person walking down a street compared to a person sitting still nearby. Clocks in different rooms of the same building can be synchronized and will, for all practical purposes, agree indefinitely. Two people can arrange to meet at a specific hour, confident that the concept of that hour arriving means the same thing for both of them regardless of what either was doing beforehand. This shared, synchronized experience of time is so consistent and so deeply embedded in ordinary life that treating it as an absolute universal fact about the structure of reality seemed less like an assumption and more like an observation. Newton was not proposing something strange or speculative. He was formalizing what appeared at every scale accessible to 17th century instruments and experience to be simply true. This intuitive picture received centuries of reinforcement, not weakening, as physics developed further. Newtonian mechanics proved extraordinarily successful, predicting the motion of planets with enough precision to anticipate the existence of Neptune before it was ever directly observed, based purely on irregularities in the orbit of Uranus that suggested the gravitational influence of an unseen body. Engineers built bridges, mills, and eventually locomotives and steam engines using calculations rooted in Newtonian assumptions about force, mass, and time, and these calculations worked consistently and reliably across an enormous range of practical applications. By the middle of the 19th century, absolute time was not merely an unquestioned philosophical assumption. It was an assumption validated again and again by technologies that functioned exactly as predicted. There seemed to be no empirical reason whatsoever to suspect that time might behave differently than the uniform, universal river Newton had described. Yet, even within this era of apparent triumph, a few thinkers raised philosophical objections to Newton's framework, objections that would later prove strangely prophetic, even though they were not grounded in the kind of empirical crisis that would eventually force physics to change course. The German philosopher and mathematician Gottfried Wilhelm Leibniz, a contemporary and rival of Newton, argued against the notion of absolute space and time on largely metaphysical grounds. Leibniz proposed instead a relational view in which space and time were not independent, freestanding entities at all, but rather systems of relationships between physical objects and events. Under this relational picture, it would make no sense to ask where the entire universe was located in some larger, absolute space, because location itself was meaningful only in relation to other objects. Similarly, it would make no sense to ask what time it was independent of any events occurring, because time itself was nothing more than the ordering of those events relative to one another. Newton and Leibniz debated these positions directly, most famously through an exchange of letters mediated by the philosopher Samuel Clarke, and the dispute was never conclusively settled by the intellectual tools available to either side. Newton's absolute framework won out, not because Leibniz's relational objections were refuted, but because Newtonian mechanics worked so well in practice that the philosophical question of what time and space fundamentally were came to seem, to most working physicists, like an unnecessary distraction from the productive business of calculation and prediction. It is a useful exercise to sit with what Newton's absolute time actually implied, stripped of the familiarity that centuries of use have layered over it, because the implications are more radical than they first appear. If time is truly absolute and universal, then there must exist, in principle, a single, well-defined answer to the question of what is happening right now across the entire universe, simultaneously, everywhere, regardless of distance. Two events, one occurring near a distant star and another occurring in a laboratory on Earth, would have a definite, objective temporal relationship to one another, a fact about which one happened first, or whether they happened at precisely the same moment, that would not depend on who was asking or how the question was being measured. This single universal simultaneity is a strong claim about the structure of reality. It assumes that some form of instantaneous, faster than any physical process, ordering exists across the entire cosmos, tying together every event everywhere into one unified, synchronized timeline. Newton did not have any direct way to test this claim across cosmic distances. It was, in his framework, simply built in as an axiom, a starting assumption rather than something derived from observation, because at the scales accessible to 17th and 18th century physics, there was no practical way to distinguish a truly universal simultaneity from one that merely appeared universal due to the limitations of available measurement. This gap between what Newtonian physics assumed and what it could actually verify would remain invisible for the better part of 2 centuries, simply because nothing in ordinary experience or available technology pushed hard enough against the assumption to reveal its weaknesses. The speeds involved in everyday life, and even in the most advanced engineering projects of the 18th and 19th centuries, were minuscule compared to the speed of light, and at such modest speeds, any relativistic effects predicted by a later, more complete theory would be so vanishingly small as to be completely undetectable with the instruments of the era. Newtonian mechanics functioned, for all practical human purposes, as though it were exactly true, because the deviations from its predictions, deviations that a later generation of physicists would eventually measure with extraordinary precision, were simply too small to register on any clock, telescope, or mechanical apparatus available at the time. The situation began to shift, gradually and then with increasing urgency, as physics turned its attention toward a phenomenon that did not fit comfortably within the Newtonian framework at all: light itself. Newton had his own theory of light, treating it as a stream of particles traveling through space, and this corpuscular theory had its own internal logic and predictive successes. But over the course of the 18th and 19th centuries, mounting evidence, including the observation of interference patterns that seem to require light behaving as a wave rather than a stream of discrete particles, gradually shifted scientific consensus toward a wave theory of light instead. This shift, seemingly a matter of settling a specific technical dispute about the nature of one particular physical phenomenon, would turn out to carry consequences far beyond what anyone initially anticipated. Waves, as understood in the 19th century, required a medium to travel through. Sound waves travel through air, through water, through solid materials, but not through the vacuum of empty space, because there is no material substance there for the wave to disturb and propagate through. If light was a wave, physicists reasoned, then it too must require some kind of medium, some substance filling all of space, including the seemingly empty vacuum between the Earth and the Sun, through which light waves could propagate in the same way that sound waves propagate through air. This reasoning led directly to the proposal of a substance called the luminiferous ether, imagined as an invisible, weightless, frictionless medium permeating the entire universe, providing the physical substrate through which light waves traveled and, crucially, providing something else as well: a fixed, absolute reference frame against which all motion, including the Earth's motion through space, could in principle be measured directly. If the ether existed and filled all of space uniformly, then the Earth, orbiting the Sun at a known and substantial speed, should be moving through this ether constantly, creating what physicists of the era sometimes described as an ether wind. Analogous to the wind, a moving vehicle experiences even on a perfectly still day, generated purely by its own motion through otherwise stationary air. Detecting this ether wind, physicists reasoned, would provide direct experimental confirmation not only of the ether's existence, but of something Newton's framework had always assumed without being able to prove: a fixed, absolute backdrop against which the true motion of any object, including the entire planet, could finally be measured. The stage was set for an experiment that would attempt exactly this measurement, an experiment whose result, rather than confirming the fixed absolute framework Newton had described, would instead deliver the first serious empirical crack in a picture of time and space that had gone unquestioned by mainstream physics for well over 200 years. By the 1880s, the tools available to experimental physics had advanced to the point where testing for the ether wind was no longer just a theoretical possibility. It had become an achievable, practical goal. The challenge lay in the scale of the effect being sought. The Earth moves through space at roughly 30 kilometers per second in its orbit around the Sun, a considerable speed by human standards, but tiny compared to the speed of light, which travels at roughly 300,000 kilometers per second. Any resulting difference in the measured speed of light, depending on whether it was traveling with or against the presumed ether wind, would be a small fraction of the total speed, requiring an instrument capable of detecting differences far too minute for any apparatus that had existed previously. The physicist Albert Michelson, working first alone and later in collaboration with the chemist Edward Morley, designed an instrument precisely suited to this task. Their apparatus, known as an interferometer, worked by splitting a single beam of light into two separate beams using a partially silvered mirror, sending each beam along a different path at a right angle to the other, before reflecting both beams back and recombining them. If both paths were of exactly equal length, and if light traveled at the same speed regardless of direction, the two beams would recombine perfectly in phase, reinforcing each other. But if the Earth's motion through the ether caused light to travel faster along one path than the other, however slightly, the recombined beams would fall very slightly out of step with one another, producing a distinctive interference pattern, a series of alternating light and dark bands that could be measured with extraordinary precision. Crucially, Michelson and Morley designed their apparatus so that it could be rotated, allowing them to test the speed of light in multiple directions relative to the Earth's motion, and they expected the interference pattern to shift measurably as the orientation changed, revealing the ether wind's influence on light's effective speed in different directions. The experiment, conducted in 1887 in Cleveland, Ohio, was sensitive enough to detect an effect many times smaller than what the ether hypothesis predicted should be easily observable. Michelson and Morley rotated their apparatus through a full range of orientations, repeating measurements carefully across different times of day and different seasons, accounting for the fact that the Earth's velocity relative to any fixed ether would change as the planet proceeded along its orbit. The result, when it came, was almost anticlimactic in its simplicity, and precisely for that reason, profoundly disruptive. No shift appeared. The interference pattern remained essentially unchanged regardless of the apparatus's orientation, within a margin far smaller than the effect the ether hypothesis demanded. Light appeared to travel at exactly the same speed in every direction, regardless of the Earth's motion through space, exactly as though there were no ether wind at all, as though the planet were not moving through any medium whatsoever, or as though the medium itself were somehow moving along perfectly with the Earth in a way that canceled out any detectable effect. This null result placed physicists in a genuinely uncomfortable position, one that is easy to underestimate in hindsight now that the resolution is well understood and thoroughly confirmed. The ether hypothesis was not an arbitrary or poorly motivated idea. It followed logically from well-established physics, from the wave theory of light and the reasonable assumption, backed by every other known example of wave phenomena, that waves require a medium through which to propagate. Abandoning the ether outright would have meant abandoning an entire framework for understanding how light could travel across the vacuum of space at all, a framework that had no obvious replacement waiting in the wings. Rather than discard the ether, most physicists of the era chose instead to modify it, proposing increasingly elaborate explanations for why the Michelson-Morley experiment had failed to detect something that theory strongly suggested should be there. Several serious proposals emerged in the years following the experiment, each attempting to preserve the ether while accounting for the stubbornly negative result. The physicist George Fitzgerald and independently the physicist Hendrik Lorentz proposed what became known as the length contraction hypothesis, suggesting that physical objects moving through the ether might actually contract slightly along the direction of their motion by precisely the amount needed to compensate for the ether wind's effect on light's travel time, thereby producing a null result, even though the ether and its associated wind genuinely existed. This proposal, now known as the Lorentz-Fitzgerald contraction, might sound at first like an ad hoc rescue of a failing theory, a mathematical patch introduced purely to explain away an inconvenient result rather than a genuine physical insight. In a sense, that assessment is fair, but the mathematics Lorentz developed to describe this contraction turned out to be remarkably close to the transformation equations that would later emerge from special relativity, a strange historical coincidence in which physicists, working to save an ultimately incorrect theory, stumbled onto mathematical relationships that would prove essential to the theory that replaced it. Other physicists proposed different rescues. Some suggested that the ether might be partially or fully dragged along with the Earth as it moved through space, an idea known as ether drag, which would explain why no relative motion between the Earth and the ether could be detected locally, since the ether near the Earth's surface would be moving along with the planet rather than remaining stationary while the Earth passed through it. This proposal, however, ran into serious difficulties when applied to other known phenomena, particularly the observed aberration of starlight, a slight, measurable shift in the apparent position of stars caused by the Earth's motion through space, which had been documented and measured with reasonable precision since the 18th century. And which behaved in a way that was difficult to reconcile with a fully or even partially dragged ether. Each attempted patch solved the immediate problem of the Michelson-Morley null result while creating new inconsistencies elsewhere, a pattern that should feel familiar to anyone who has watched a scientific framework strain under the weight of an anomaly it was never designed to accommodate. The ether hypothesis was not being disproven all at once through some single decisive experiment. It was being slowly worn down, patched repeatedly, each patch a little more elaborate and a little less satisfying than the last. By the early years of the 20th century, the ether had become a theoretical construct sustained more by the absence of an alternative than by any positive, direct evidence in its favor. Repeated experiments, refining and extending the basic Michelson-Morley setup with ever greater precision, continued to find no trace of the predicted ether wind. The contraction hypothesis proposed by Lorentz and Fitzgerald could account for the null result mathematically, but it offered no clear physical mechanism explaining why matter should contract in exactly this way, along exactly this axis, by exactly the amount needed to preserve the ether's existence. It had the uncomfortable feel of a theory rescued through a mathematical trick rather than a genuine physical insight, a pattern where the equations worked, but the underlying story they were supposed to be telling no longer made intuitive sense. Physicists were left with a stable, precisely repeatable experimental result, the constancy of light's measured speed regardless of direction or the observer's motion, and no framework within existing physics that could explain this result without resorting to increasingly strained and unmotivated auxiliary assumptions. It is worth pausing to consider what made this situation genuinely difficult, rather than simply a matter of physicists being slow to accept an obvious answer. The obvious answer, in hindsight, is that there is no ether and that light speed really is constant for every observer, regardless of their own motion, a fact built into the basic structure of the universe rather than something requiring a medium to explain. But accepting this answer meant accepting something that seemed to violate basic, well-tested principles of how velocities combine, principles that worked reliably for every other kind of motion physicists had ever measured, from thrown balls to speeding trains to orbiting planets. If a train is moving at a certain speed, and someone aboard that train throws a ball forward at some additional speed, an observer standing outside the train, watching it pass, measures the ball's total speed as the sum of the train speed and the ball's thrown speed relative to the train. This is not a special case or an approximation. It follows directly from the basic, intuitive, and repeatedly confirmed way that velocities are supposed to add together under classical mechanics. If light behaved the same way, its measured speed should have varied depending on the motion of its source and the motion of the observer measuring it, exactly the way the ball's speed varies depending on the train's motion. The Michelson-Morley result suggested that light simply did not follow this rule, that its speed remained fixed and constant no matter what, a finding that could only be reconciled with the rest of physics by abandoning something physicists had never previously considered negotiable: the assumption that measurements of space and time themselves were absolute and independent of an observer's own state of motion. This is precisely the assumption that a young examiner at the Swiss Patent Office in Bern would soon challenge directly, not by proposing a more elaborate patch to the ether hypothesis, but by taking the null result of the Michelson-Morley experiment, along with the broader implication that light speed appears constant for every observer, entirely at face value, and following that implication through to its full and startling logical conclusion, regardless of how strange the resulting picture of space and time might appear. Where Lorentz had modified the mathematics of moving objects while preserving the underlying ether framework, this new approach would dispense with the ether altogether, treating the constancy of light speed not as a puzzle to be explained away, but as a fundamental starting point from which everything else, including the very structure of space and time, would need to be reconstructed. In 1905, working outside the traditional structures of academic physics, Albert Einstein published a paper that approached the unresolved crisis differently from everyone who had come before him. Rather than searching for a more sophisticated way to preserve the ether, he asked a more fundamental question. What if the null result of the Michelson-Morley experiment was not a puzzle requiring an elaborate physical explanation, but a straightforward statement of fact about how the universe is built. What if light truly does travel at the same speed for every observer, regardless of their own motion, not because some hidden mechanism conspires to disguise a variation that is really there, but because no such variation exists in the first place? Einstein took this possibility seriously, and rather than treating it as an anomaly to be explained away, he adopted it as a foundational assumption and asked what else would have to be true about the universe for this assumption to hold consistently, without contradiction, across every possible situation. The resulting theory, special relativity, rested on two postulates, each stated with a plainness that belies the magnitude of what follows from them. The first postulate holds that the laws of physics are identical for all observers moving at constant velocity relative to one another. No observer's frame of reference is privileged. A physicist conducting an experiment aboard a smoothly moving train obtains exactly the same results, following exactly the same laws, as a physicist conducting an identical experiment on a stationary platform. This idea was not new. A version of it traces back to Galileo, who noted that a ship moving smoothly across calm water offers no internal mechanical experiment capable of revealing its own motion to a passenger confined below deck. Einstein's second postulate, however, broke sharply from everything that had come before. It states that the speed of light in a vacuum is the same for every observer, regardless of the motion of the light source and regardless of the observer's own motion. A person standing still and a person sprinting directly toward a beam of light will measure that beam traveling at exactly the same speed, a result that violates the basic intuitive rule of velocity addition that governs virtually every other kind of motion in ordinary experience. Taken together, these two postulates seem almost too simple to generate the sweeping consequences that follow from them. And yet their combination forces a reconstruction of some of the most basic assumptions in physics. Consider what it actually means for two observers, moving at different velocities relative to each other, to measure the same beam of light traveling at the same fixed speed. Speed is calculated as distance divided by time. If two observers disagree about their own relative motion, but must agree on the speed of a passing beam of light, then something about their individual measurements of distance and time has to differ between them in a very specific and mathematically constrained way, precisely so that the ratio of distance to time comes out identical for both, despite their differing states of motion. Einstein's insight was to follow this logical requirement through to its full conclusion, rather than treating it as an uncomfortable technical detail to be minimized. If the speed of light must remain constant, then space and time themselves cannot be the fixed, absolute, universally agreed upon quantities that Newton had assumed. They must instead be flexible, adjusting in a coordinated way between observers in relative motion, specifically in whatever manner is required to keep light's measured speed constant for everyone. This reasoning led Einstein to derive a set of mathematical relationships, now known as the Lorentz transformations, describing exactly how measurements of space and time convert between observers moving at different velocities relative to one another. Notably, these were very close to the equations Hendrik Lorentz had already developed in his attempts to rescue the ether hypothesis, a detail that highlights just how close physics had already come to the correct mathematics without yet arriving at the correct physical interpretation. Lorentz had derived his transformations as a mechanical patch, a way of explaining why moving objects should physically contract in order to preserve an underlying undetectable ether. Einstein derived essentially the same mathematics from a completely different starting point, treating the transformations not as evidence of a hidden physical contraction caused by motion through some invisible medium, but as a direct, necessary consequence of the true relative nature of space and time themselves. There was no ether needed in Einstein's formulation. There was no hidden mechanism straining to disguise absolute motion. Space and time simply behaved this way, intrinsically, for every observer, without requiring any additional physical substance to explain why. The practical consequences of this reformulation followed immediately and inescapably from the mathematics. If space and time adjust between observers in relative motion, then several properties long assumed to be fixed and absolute turn out instead to depend on an observer's own state of motion. A clock moving at high velocity relative to a given observer will be measured by that observer as running slower than an identical clock at rest relative to them, an effect called time dilation. This is not a matter of the moving clock malfunctioning, nor is it an illusion created by the finite time it takes light to travel from the clock to the observer's eye. It is a genuine difference in the rate at which time itself elapses, as measured from different frames of reference, and it applies to every physical process, not merely to mechanical clocks. Biological aging, radioactive decay, chemical reactions, every process that unfolds over time will be measured as slowed from the perspective of a relatively stationary observer when that process occurs aboard an object moving at a significant fraction of the speed of light. Alongside time dilation comes a companion effect called length contraction, in which an object's measured length along its direction of motion appears shortened from the perspective of an observer relative to whom the object is moving, an effect mathematically related to the same underlying transformations and, notably, numerically identical to the contraction Lorentz and Fitzgerald had proposed years earlier for entirely different reasons. What makes Einstein's approach so different from the earlier ether-based rescues is not merely that it arrived at similar mathematics through a different route, but that it eliminated the need for any additional physical substance, any hidden medium, any undetectable absolute frame of reference against which true motion could, in principle, be measured. Under special relativity, there simply is no such frame. There is no universal now against which every event in the cosmos can be measured and ordered. There is no fixed backdrop of absolute space through which the Earth moves at some measurable, definite speed, separate from its speed relative to the Sun or the galaxy or any other chosen reference point. Motion, under this new framework, is entirely relative. It only makes sense to speak of an object's velocity in relation to some other object or observer, never in relation to space itself, considered as some kind of independent, motionless stage. This represented a genuinely radical departure from over 2 centuries of physics built on exactly the opposite assumption, and it did so not by adding new entities to explain an anomaly, but by removing an assumption that had never actually been directly verified in the first place. An assumption so deeply embedded in ordinary intuition that almost no one had previously considered it optional. The most immediately unsettling consequence of this framework concerns simultaneity itself, the very question of what counts as happening at the same time. Under Newtonian physics, simultaneity was assumed to be absolute. If 2 events occur at the same moment, according to one observer, then they occur at the same moment according to every observer everywhere, regardless of their own motion. Special relativity dismantles this assumption directly and unavoidably. Because measurements of time itself differ between observers in relative motion, 2 events that appear simultaneous to one observer will not, in general, appear simultaneous to a second observer moving at a different velocity relative to the first. This is not a matter of one observer being mistaken due to the delay of light traveling from the events to their respective locations, a factor that can be calculated and corrected for separately. It reflects a genuine, physical disagreement about the temporal ordering of distant events, a disagreement built into the very structure of how time and space relate to one another for observers in different states of motion. 2 events separated by enough distance can be measured as simultaneous by one observer, as event 1 occurring before event 2 by a second observer, and as event 2 occurring before event 1 by a third observer, with none of the 3 observers being incorrect. Each is measuring accurately within their own frame of reference. There simply is no additional, more fundamental fact of the matter capable of settling which ordering is the true one, because no such fact exists within the structure special relativity describes. This was, and remains, the single most disruptive consequence of Einstein's 1905 paper, more disruptive in its way than time dilation or length contraction, because it strikes directly at intuitions about causality, sequence, and the shared universal present that ordinary experience seems to confirm at every waking moment. If simultaneity itself depends on an observer's state of motion, then the concept of a single, universal now, ticking forward identically for the entire universe, cannot be sustained as a meaningful physical fact. It can persist at most as a convenient local approximation, useful and essentially accurate for observers moving slowly relative to one another across short distances, which describes the entirety of ordinary human experience and explains why the relativity of simultaneity remained completely undetected for so many centuries of careful observation and measurement. But at higher relative velocities, or across sufficiently vast distances, the approximation breaks down entirely, revealing a universe in which agreement about what is happening right now, everywhere, is not a stable, objective fact waiting to be discovered through sufficiently precise measurement, but rather a question whose answer genuinely depends on who is asking and how they happen to be moving relative to everything else. This raises an immediate and pressing question, one that would occupy physicists for years following Einstein's original paper. If two clocks, initially synchronized and side by side, are separated, with one remaining at rest while the other travels at high speed and eventually returns, what happens when they are brought back together and compared directly? Does the moving clock genuinely register less elapsed time than the one that stayed behind? And if so, can this effect actually be measured directly using real clocks, rather than remaining a purely theoretical prediction confined to the mathematics of an elegant but as yet unverified theory? The question posed at the close of Einstein's original paper was not allowed to remain purely theoretical for very long, though it would take decades before technology advanced to the point where a direct, controlled test became genuinely possible. The challenge was one of scale. Time dilation, as predicted by special relativity, becomes significant only as an object's speed approaches a substantial fraction of the speed of light. At the velocities available to 19th and early 20th century transportation, trains, ships, even the fastest artillery shells of the era, the predicted effect was so vanishingly small that no clock built at the time could have detected it, even in principle. Confirming time dilation directly would require either velocities far beyond anything achievable by ordinary vehicles, or clocks of a precision that did not yet exist, or, as it eventually turned out, both. The first meaningful experimental confirmations came not from macroscopic objects like trains or aircraft, but from the subatomic realm, where particles could be accelerated to speeds approaching that of light, using equipment far more practical to build than any vehicle capable of comparable velocities. Muons, unstable subatomic particles produced when cosmic rays strike the upper atmosphere, provided one of the earliest and most striking natural tests. Muons decay rapidly, with a well-established average lifetime, measured in a laboratory setting where the muon is at rest relative to the measuring equipment, of only a few millionths of a second. Given this short lifetime and the muon's velocity, even at speeds close to the speed of light, classical physics predicts that the overwhelming majority of muons created in the upper atmosphere should decay long before reaching the Earth's surface, given the distance involved. And yet, detectors placed at ground level consistently measured far more muons arriving than classical calculations predicted should survive the journey. Special relativity offered a direct and precise explanation. From the perspective of an observer on the ground, the muon's internal clock, the process governing its decay, runs measurably slower due to its high velocity, extending its effective lifetime enough to allow a much larger fraction to reach the surface than non-relativistic calculations would suggest. When physicists compared the actual number of muons detected against the number predicted using relativistic time dilation, the measured results matched the relativistic prediction closely, providing one of the earliest pieces of experimental evidence supporting Einstein's theory using naturally occurring particles rather than any built apparatus. Muon decay offered compelling evidence, but it involved subatomic particles behaving in ways that, while measurable, remained somewhat abstract and removed from everyday human experience. A more direct, tangible test would require comparing actual clocks, the kind that measure time in a way immediately relatable to ordinary human life, moved at high but achievable speeds and then compared against a stationary reference. This became possible with the development of cesium atomic clocks in the mid-20th century, instruments precise enough to measure time differences far smaller than any mechanical or quartz-based clock could reliably detect. Cesium atomic clocks work by measuring the extremely regular oscillation frequency of cesium atoms transitioning between specific energy states, a frequency so stable and consistent that it eventually became the international standard definition of the second itself. With clocks this precise, physicists finally possessed instruments capable of detecting time dilation effects at speeds achievable by ordinary aircraft, speeds far below what would be needed to produce dramatic differences, but fast enough to produce a small, measurable effect given sufficiently accurate instruments and sufficiently careful experimental design. In 1971, physicists Joseph Haffel and Richard Keating conducted an experiment that has since become one of the most frequently cited direct confirmations of relativistic time dilation involving macroscopic human-scale objects. They placed cesium atomic clocks aboard commercial airliners and flew them around the world, first traveling eastward and then, on a separate journey, traveling westward, while a set of reference clocks remained stationary at the United States Naval Observatory. Special relativity predicts a subtle but calculable difference between these scenarios because the eastward flight adds to the Earth's own rotational velocity while the westward flight subtracts from it, meaning the clock traveling eastward moves faster relative to the Earth's center and should therefore experience slightly more time dilation, while the westward traveling clock moves relatively slower and experiences slightly less. General relativity adds a further complication. Since the airborne clocks also experience a weaker gravitational field at altitude compared to the clocks on the ground, an effect that works in the opposite direction, causing clocks at higher altitude to run comparatively faster due to their reduced gravitational influence. Calculating the combined prediction required accounting for both effects simultaneously, producing a specific, numerically precise expectation for how much the flown clocks should differ from the stationary reference clocks once reunited. When Haffel and Keating compared the clocks after their respective journeys, the measured differences matched the combined relativistic predictions closely, falling within the margin of experimental uncertainty associated with the atomic clocks available at the time. The eastward flying clock lost a small but measurable amount of time relative to the ground-based reference, while the westward flying clock gained a small but measurable amount, exactly the pattern predicted once both the velocity-based time dilation from special relativity and the gravitational time dilation from general relativity were properly combined. This experiment has since been criticized on methodological grounds by some commentators, given the limited precision of the atomic clocks available in 1971 and the relatively small magnitude of the predicted effects compared to the instrument's margin of error. But subsequent experiments using more advanced and more precise atomic clocks have repeated similar tests with significantly tighter error margins, and the results have continued to confirm the same basic relativistic predictions with increasing confidence. What began as a somewhat improvised experiment involving commercial airline tickets and clocks strapped into passenger seats has since evolved into a well-established and thoroughly repeated category of experimental confirmation, one that no longer rests on any single measurement, but on an accumulated body of evidence collected across many decades using progressively more sophisticated instruments. Perhaps the most consequential and continuous confirmation of relativistic time dilation, however, comes not from a specific historical experiment conducted for the purpose of testing relativity, but from a piece of infrastructure that operates constantly, silently, in the background of modern civilization: the Global Positioning System. GPS satellites orbit the Earth at an altitude of roughly 20,000 kilometers, moving at a velocity of approximately 14,000 kilometers per hour relative to the surface. At this velocity, special relativity predicts that the atomic clocks aboard each satellite should run measurably slower than identical clocks on the ground due to their high orbital speed. At the same time, because the satellites orbit at a significant altitude, they also experience a considerably weaker gravitational field than clocks at the Earth's surface, and general relativity predicts that weaker gravity causes clocks to run comparatively faster, an effect that operates in the opposite direction from the velocity-based slowing, and, at the orbital altitude used by GPS satellites, turns out to be larger in magnitude. When both effects are calculated together, the net prediction is that clocks aboard GPS satellites should run faster than identical clocks on the ground by an amount that, while extremely small in absolute terms, becomes significant given the extraordinary precision required for accurate satellite positioning. The specific figure involved is worth stating plainly, because its consequences illustrate just how seriously modern engineering takes these relativistic corrections. Left uncorrected, the combined relativistic effects would cause GPS satellite clocks to gain roughly 38 microseconds per day relative to ground-based clocks, a duration that sounds negligible until translated into positioning error, because GPS positioning relies on precisely timing how long radio signals take to travel from satellites to a receiver on the ground. And because those signals travel at the speed of light, even a tiny timing discrepancy translates directly into a substantial positioning error. A timing error of 38 microseconds, left uncorrected and allowed to accumulate, would produce positioning errors on the order of 10 kilometers per day, an error that would render the entire GPS system essentially useless for navigation within a matter of hours. To prevent this, engineers built relativistic corrections directly into the GPS system's fundamental design, adjusting the rate at which the satellite clocks tick before they are ever launched into orbit, so that once relativistic effects are factored in, the satellite clocks align correctly with ground-based time as experienced by receivers on Earth. This is not a theoretical curiosity confined to physics departments. It is functioning, load-bearing engineering relied upon continuously by billions of people navigating with smartphones, aircraft relying on precise positioning for safe flight paths, and financial systems that depend on precisely synchronized timestamps for transactions occurring across the globe. Every time a navigation app correctly displays a person's location, it is quietly relying on the assumption that time does not pass at the same rate for a satellite in orbit as it does for a person standing on the ground, an assumption confirmed continuously every day by the simple fact that the system works. Taken together, these lines of evidence, from the decay rates of subatomic particles produced by cosmic rays to atomic clocks flown around the world aboard commercial airliners to the everyday functioning of satellite navigation systems, converge on the same conclusion from entirely independent directions. Time dilation is not a mathematical curiosity confined to abstract equations, nor is it a subtle effect visible only under highly specialized laboratory conditions. It is a measurable, repeatedly confirmed feature of how the universe actually operates, verified across scales ranging from subatomic particles to orbiting spacecraft, using measurement techniques developed decades apart by researchers with no particular stake in confirming one another's results. Clocks moving at different velocities relative to one another, and clocks situated in different gravitational environments, genuinely tick at different rates, not due to any mechanical flaw or measurement error, but because the flow of time itself, if it can even still be called a flow, depends on the specific path an object takes through the four-dimensional structure of spacetime. This raises a question that becomes increasingly difficult to avoid the more deeply one considers what these confirmed effects actually imply. If two clocks, starting synchronized, can be separated and reunited with a definite, measurable, and asymmetric difference in elapsed time between them, what does this reveal about the nature of duration itself, about what it actually means for time to pass for any given object moving along its own particular path through the universe? This question, seemingly a simple extension of the clock experiments already described, leads directly into one of the most famous and frequently misunderstood thought experiments in all of physics, one involving a pair of twins, a journey through space, and a disagreement about elapsed time so stark that it would eventually force physicists to reconsider what aging itself actually means within a universe where time no longer flows the same way for everyone. Consider two twins born on the same day, one of whom remains on Earth while the other boards a spacecraft capable of reaching a significant fraction of the speed of light, travels to a distant star system, and returns. Special relativity makes a definite and testable prediction about what happens when the traveling twin steps back onto Earth. The twin who stayed behind will have aged more than the twin who made the journey. This is not a difference in appearance or a trick of memory. It is a genuine difference in elapsed time, in the number of heartbeats, the number of thoughts, the number of physical and biological processes that occurred for each twin between departure and reunion. The traveling twin has not been frozen or slowed in any mechanical sense. From their own perspective, time passed entirely normally at its usual unremarkable pace. And yet, upon return, less of it will have passed for them than for the twin who remained behind. This scenario has earned the label of a paradox largely because of an apparent symmetry that turns out, on closer inspection, to be illusory. Motion, after all, is relative. From the perspective of the traveling twin, one might argue, it is the earthbound twin who is moving away and then returning, not the other way around. And so, by the same logic that predicts the traveling twin ages less, should it not equally be true that the earthbound twin ages less from the traveler's frame of reference? If both predictions were simultaneously true, the situation would indeed be paradoxical, an actual logical contradiction rather than merely a counterintuitive result. But the two situations are not symmetric, and the resolution of this apparent paradox turns out to depend precisely on the kind of four-dimensional thinking that the mathematician Hermann Minkowski introduced into physics only a few years after Einstein's original paper, thinking that transforms the twin scenario from a puzzling verbal argument into a straightforward geometric fact. The asymmetry lies in acceleration. The earthbound twin remains in a single, unchanging state of motion throughout the entire scenario, technically referred to as an inertial frame, never speeding up, slowing down, or changing direction. The traveling twin, by contrast, must accelerate away from Earth at the start of the journey, decelerate and reverse direction at the distant destination, and decelerate again upon returning home. These changes in velocity break the symmetry between the two twins in a way that special relativity's mathematics captures precisely, even though describing exactly why requires moving beyond simple verbal reasoning about relative motion and into the geometric structure that Minkowski had proposed. Rather than treating the paradox as a matter of whose perspective counts as truly moving, Minkowski's framework reframes the entire scenario in terms of the paths each twin traces through four-dimensional spacetime, and it is within this reframing that the puzzle dissolves entirely, replaced by a result as unambiguous as any measurement in physics. Recall the central idea introduced by Minkowski at that lecture in Cologne, where he proposed treating space and time not as separate, independently ticking quantities, but as a single unified four-dimensional structure. Within this structure, every object traces out a continuous path as it persists through time, a path called a world line, extending from the moment of the object's creation to the moment of its destruction, or, for a person, from birth to death. The earthbound twins' world line is, geometrically speaking, a straight line through space-time, since their velocity never changes. The traveling twins' world line, by contrast, bends, first angling away from the earthbound twins' straight path as the spacecraft accelerates, then angling back as it decelerates and reverses course, and then angling once more as it decelerates upon return. This bending is the geometric signature of the acceleration the traveling twin experiences, and it is directly responsible for the difference in elapsed time between the two paths. Here, a further consequence of the peculiar geometry of spacetime becomes essential, one that runs directly against the intuitions built up from ordinary three-dimensional geometry. In everyday space, the shortest distance between 2 points is a straight line, and any path that bends or curves between the same 2 points is necessarily longer than the straight one. In spacetime, remarkably, the relationship is reversed for the specific quantity that corresponds to elapsed time along a world line. Because the mathematics of spacetime distance involves that crucial subtraction between spatial and temporal components rather than the simple addition used in ordinary geometry, a straight world line between two events in spacetime actually corresponds to the greatest possible elapsed time, while any bent or curved path between the same two events corresponds to less elapsed time. The earthbound twin, tracing the straight path, experiences the maximum possible elapsed time between departure and reunion. The traveling twin, whose path bends through spacetime due to acceleration, experiences less. This is not a paradox once expressed in these geometric terms. It is simply a consequence of the shape of the two paths taken through a four-dimensional structure whose geometry differs in this crucial respect from the geometry of ordinary space. The twin paradox, properly understood, offers one of the clearest illustrations of why Minkowski's reformulation mattered so profoundly, and why Einstein, initially resistant to what he considered an unnecessary mathematical complication, eventually came to regard it as indispensable. Special relativity, expressed purely in terms of separate transformations for space and separate transformations for time, makes correct predictions, but it can make those predictions feel arbitrary, a set of disconnected rules that happen to produce consistent results without offering much insight into why those particular rules should hold. Minkowski's geometric approach reveals the underlying unity. Time dilation, length contraction, the relativity of simultaneity, and the resolution of the twin paradox are not four separate phenomena requiring four separate explanations. They are all consequences of a single underlying fact, that space and time together form a four-dimensional structure with a specific geometric shape, one in which the separation between any two events can be measured using an invariant quantity that remains the same for every observer, regardless of their own state of motion, even though individual observers will disagree about how that invariant separation splits between spatial distance and temporal duration. This invariant quantity, the space-time interval, deserves closer attention because it is the single mathematical object that makes sense of everything the twin paradox illustrates. Ordinary geometric distance in three-dimensional space is calculated by combining the differences in each spatial coordinate using addition, following a rule familiar from the Pythagorean theorem taught in every introductory geometry class. The space-time interval follows a superficially similar formula, but with a critical difference. The temporal component enters the calculation with an opposite sign from the spatial components, effectively subtracted rather than added. This single change in sign has enormous consequences. It means that the space-time interval between two events can be dominated by either the spatial separation or the temporal separation, depending on which is larger, and events separated primarily by time, like the two moments marking a single object's continued existence at rest, behave very differently under this geometry than events separated primarily by space, like two simultaneous but distant occurrences. It is this same sign difference that produces the reversal in which straight world lines correspond to maximum elapsed time rather than minimum distance, and understanding this single mathematical detail unlocks a coherent, unified picture of nearly every strange relativistic effect that otherwise seems to arrive as an isolated, disconnected rule. The deeper implication of Minkowski's framework, the one most directly relevant to the central argument of this investigation, concerns what it means for something to exist within a four-dimensional structure of this kind. In ordinary three-dimensional space, no one considers a distant city to be less real simply because they are not currently standing in it. Lisbon does not blink out of existence for a person standing in Tokyo, and Tokyo does not blink out of existence for a person standing in Lisbon. Each city simply occupies a different region of the same shared spatial structure, equally real, equally present, differing only in their location relative to any given observer. Minkowski's insight was to demonstrate, through rigorous mathematics rather than philosophical assertion, that time behaves in a structurally similar way once properly understood as a dimension woven together with space rather than a separately flowing quantity layered on top of it. Your birth and your death occupy different regions of the four-dimensional structure in the same way that Lisbon and Tokyo occupy different regions of three-dimensional space. Neither event is privileged simply because your consciousness at this particular moment happens to be located at a point in space-time somewhere between the two. This is precisely the picture that gives the block universe hypothesis its name and its mathematical foundation. If space-time is a single unified four-dimensional structure, and if every world line within that structure, from the path of a subatomic particle to the path of an entire human life, is already complete, extending from beginning to end as a fixed geometric object rather than something being drawn moment by moment as time passes, then the entire history of the universe, past, present, and future alike, exists as a single unchanging block. The twin paradox, resolved through careful attention to the shape of two different world lines through this block, offers a striking demonstration of just how literally physicists mean this claim. The two twins do not experience different amounts of time passing because time itself sped up or slowed down for one of them in some mysterious dynamic sense. They experience different amounts of elapsed time because their world lines, fixed and complete within the four-dimensional structure of spacetime, simply have different lengths, measured using the peculiar geometry that governs how space and time combine. If world lines are geometric objects with definite shapes and definite lengths, existing as complete structures within a four-dimensional block, what does that imply about the objects tracing them, and about the strange asymmetric boundary that determines which events in this block can possibly influence which others? Every world line traced through the four-dimensional block obeys a constraint so fundamental that it shapes the entire causal structure of the universe, and that constraint traces directly back to the second postulate of special relativity. Nothing with mass can travel at or beyond the speed of light, and light itself, moving through a vacuum, always travels at exactly that fixed speed, regardless of the motion of whatever emitted it. This single limit, seemingly a narrow technical restriction on velocity, turns out to carve the entire four-dimensional structure of spacetime into distinct regions that determine for any given event precisely which other events could possibly have caused it and which other events it could possibly go on to influence. Physicists visualize this structure using a construction known as the light cone, and understanding its shape is essential to understanding how causality itself is built into the geometry of the block universe. Picture a single event, a brief flash of light occurring at a specific point in space and at a specific moment in time. From that single point, light radiates outward in every possible direction simultaneously, expanding as a sphere that grows larger each moment, its radius increasing at the fixed, unvarying speed of light. If this expanding sphere is plotted not just in three-dimensional space, but across time as well, using the fourth dimension to represent the moment-by-moment growth of the sphere, the resulting shape is a cone, its point located at the original flash of light, its surface expanding outward and forward in time. This is called the future light cone, and it defines the absolute boundary of everywhere that a signal originating at that single event could possibly reach, given that nothing can travel faster than light itself. Any event lying within this cone, closer to the central axis than to the outer surface, is potentially reachable by some influence originating from the original flash, whether that influence travels at the speed of light itself or at some slower speed. Any event lying entirely outside this cone, however, can never be reached by any signal originating from the flash, regardless of how much time passes, because doing so would require traveling faster than light, a possibility special relativity firmly excludes. A symmetrical structure exists in the other temporal direction as well, called the past light cone, tracing backward from the same central event to encompass every possible location from which a signal traveling at or below the speed of light could have originated in time to reach that event. Together, the future light cone and the past light cone divide the entirety of spacetime relative to any given event into distinct and clearly defined categories. Events within the past light cone could potentially have influenced the central event, having had time for a signal to travel from their location to the location of the central event without exceeding the speed of light. Events within the future light cone could potentially be influenced by the central event for the same reason applied in the opposite temporal direction. And then there's a third category, often the most conceptually challenging to grasp fully, consisting of every event that lies outside both cones entirely, a region physicists sometimes call elsewhere, or more technically, space-like, separated from the central event. Events that are space-like separated from one another share a peculiar and important property. No signal, no influence, no cause and effect relationship of any kind can connect them in either temporal direction without violating the speed of light limit. This means that for two space-like separated events, there exists no absolute, universally agreed upon fact about which one happened first. Recall the earlier discussion of the relativity of simultaneity. the finding that observers in relative motion can disagree about which of two events occurred earlier. That disagreement, it turns out, is only possible and only meaningful when the two events in question are space-like separated from one another. If two events are time-like separated, meaning one lies within the other's light cone, every observer, regardless of their own state of motion, will agree on which event happened first, because a causal influence could genuinely have traveled from the earlier event to the later one, and causality, unlike simultaneity, is preserved absolutely across every possible observer under special relativity. It is only for events far enough apart in space, relative to the time separating them, that no signal could possibly connect them, that the question of temporal order becomes observer-dependent, with different observers moving at different velocities, legitimately disagreeing about which of the two events came first, and neither being mistaken. This structure resolves what might otherwise seem like a serious threat to the entire framework of physics. If simultaneity is relative, and if different observers can disagree about the order of events, does this not open the door to violations of causality, to scenarios in which an effect might be measured by some observer somewhere as occurring before its own cause? The light cone structure closes this door completely. Causally connected events, meaning any pair of events where one could plausibly have caused the other, are always time-like separated, always lying within each other's light cones, and the order of time-like separated events is absolute, agreed upon by every observer without exception, regardless of their relative motion. The relativity of simultaneity applies only to space-like separated events, events too far apart in space, given the time between them, for any causal influence to have passed between them in the first place. Since no cause and effect relationship could exist between such events regardless of their temporal ordering, disagreement about which one happened first carries no threat to causality, because neither event was ever in a position to cause the other. The universe, in other words, is built with a kind of built-in safeguard, a structural feature of space-time geometry itself that permits the relativity of simultaneity to operate freely without ever allowing an effect to precede its own cause for any observer, anywhere. This light cone structure carries a striking implication for how physicists think about the shape and content of the observable universe itself. Every observer, at every point in space-time, is effectively confined to their own past light cone when it comes to gathering information about the rest of the universe. You cannot see, measure, or receive any signal from an event that lies outside your past light cone, because no signal from such an event has had time to reach you, given the finite speed of light and the distances involved. This is why astronomers speak of looking into the past whenever they observe distant objects in the night sky. The light reaching a telescope from a galaxy several billion light-years away departed that galaxy several billion years ago, meaning astronomers are not observing that galaxy as it exists now in any meaningful simultaneous sense, but as it existed at the moment the observed light began its journey. In a very literal, physically precise sense, looking outward into space is equivalent to looking backward in time, deeper and deeper into the past light cone, with more distant objects corresponding to earlier and earlier points along that cone's surface. There is no way to observe a distant event as it is happening now, in any sense that would satisfy Newton's assumption of absolute universal simultaneity, because now, in that absolute sense, does not exist as a physically meaningful concept once light cones are taken seriously as the actual causal structure of the universe. This observation connects directly back to the deeper question this investigation has been building toward. If every event's world line is a fixed geometric object within the four-dimensional block, and if the light cone structure at every point in space-time is similarly fixed, determined entirely by the unchanging speed of light and the geometry Minkowski described, then the entire causal structure of the universe, the complete network of which events could have influenced which others, already exists as a static, unchanging feature of the block, rather than something that comes into being progressively as time unfolds. The light cone, belonging to any given event, does not grow or expand as time passes in some dynamic sense. It is already there, complete, a fixed geometric feature of that event's location within spacetime, in the same way that the borders of a country are already fixed on a map regardless of whether anyone is currently looking at that particular region of the map. What changes under this view is not the structure itself, but which portion of that structure a given conscious observer happens to be experiencing at any particular moment, their own position sliding or seeming to slide along their own world line through a landscape whose shape and causal connections were never actually in flux to begin with. It is worth pausing here to address a natural objection, one that arises almost immediately upon encountering this picture for the first time. If the light cone structure is fixed, and if causality is absolute within time-like separated events, does this not suggest a fully deterministic universe, one in which the future is not merely real in some abstract four-dimensional sense, but actually fixed and inevitable, following necessarily from the past with no room remaining for genuine chance, uncertainty, or choice? This question deserves careful treatment, and it will be addressed directly later in this investigation, once the strange behavior of quantum mechanics has been examined, since quantum theory introduces genuine complications to any simple, fully deterministic reading of the block universe picture. For now, it is enough to note that the light cone structure describes what is causally possible, the boundaries within which influence can travel, rather than making any claim by itself about whether everything within those boundaries proceeds according to a single, predetermined outcome. The relationship between the fixed geometry of spacetime and the question of determinism turns out to be considerably more subtle than it first appears, and untangling that subtlety requires first confronting one further, deeply strange feature of special relativity, one that emerges directly from everything already established about light cones and relative simultaneity. A thought experiment involving nothing more dramatic than a person taking an ordinary walk and a distant galaxy whose present moment shifts, according to the mathematics, by more than a full day, depending on nothing more than the direction and speed at which that person happens to be moving. The thought experiment, now known as the Andromeda paradox, was introduced by the physicist Roger Penrose and later popularized by the philosopher of science Michael Reitdijk, and independently by Hilary Putnam, though its clearest and most widely cited formulation belongs to Penrose. Its purpose is to take the abstract mathematics of relative simultaneity, already established through the Lorentz transformations and the light cone structure, and translate it into a scenario vivid enough that its full strangeness becomes impossible to avoid. The scenario requires nothing exotic. No spacecraft traveling near the speed of light, no advanced technology, no laboratory instruments of any kind. It requires only two people standing near each other on a street and a galaxy roughly 2.5 million light-years away. Consider two observers standing side by side, one of them momentarily at rest, the other walking past at an ordinary, unremarkable walking pace, perhaps 5 kilometers per hour. Both observers are looking, in their imagination, if not literally with their eyes, toward the Andromeda galaxy, the nearest large spiral galaxy to our own, separated from Earth by a distance so vast that light itself takes roughly 2.5 million years to cross it. According to special relativity, each observer can construct what is called a plane of simultaneity, a mathematical surface representing every event throughout the entire universe that they consider to be happening right now, at this particular moment, given their own current position and their own current velocity. For the observer standing still, this plane of simultaneity is tilted one way relative to Andromeda. For the observer walking, moving at even this modest, thoroughly ordinary speed, the plane of simultaneity is tilted very slightly differently, because their velocity relative to Andromeda differs, however slightly, from the velocity of the observer standing still. The tilt involved is genuinely minuscule, a product of the enormous ratio between walking speed and the speed of light, and at the scale of everyday distances, this tilt produces no detectable difference at all in what counts as simultaneous. But Andromeda is not an everyday distance. It sits roughly 2.5 million light-years away, and across a distance that vast, even the smallest possible tilt in the plane of simultaneity translates into an enormous difference in which events on or near Andromeda each observer would consider to be happening right now. Working through the actual mathematics of the Lorentz transformations, using the walking observer's modest velocity and Andromeda's immense distance, produces a genuinely striking result. The event on Andromeda that the walking observer would consider simultaneous with the present moment differs from the event the stationary observer would consider simultaneous with that same moment by an interval that can amount to several days, depending on the exact walking speed and direction chosen for the calculation. Simply by beginning to walk, by shifting from standing still to moving at an ordinary human pace, an observer's plane of simultaneity sweeps across several days' worth of events unfolding on a galaxy millions of light years away, days that, for the observer standing still beside them, were not yet included as part of the present moment at all. It is worth sitting with exactly what this thought experiment does and does not claim, because it is easy to misread it as suggesting something physically implausible, some kind of genuine causal influence transmitted instantaneously across millions of light years merely by a person choosing to walk. This is not what the Andromeda paradox demonstrates, and clarifying the distinction matters considerably for understanding what the thought experiment actually reveals about the structure of spacetime. No information passes between the walking observer and Andromeda. No signal, no influence, no physical effect of any kind travels across that vast distance as a result of the observer's change in velocity. The walking observer does not somehow gain instantaneous knowledge of events on Andromeda that the stationary observer lacks, nor does the walking observer's decision to move somehow alter what is actually happening on that distant galaxy. What changes is not any physical fact about Andromeda itself, but rather which set of already existing events on Andromeda gets labeled as simultaneous with the observer's own present moment, a labeling exercise that depends entirely on the observer's own state of motion and carries no causal weight whatsoever. This distinction between a genuine causal influence and a mere relabeling of which distant events count as simultaneous is precisely the distinction the light cone structure, established earlier in this investigation, was designed to preserve. Andromeda and the two observers on Earth are separated by such an enormous, space-like interval, given the distance involved, that no event on Andromeda and no event involving the two Earth-bound observers could possibly stand in any causal relationship to one another across the timescales relevant to this thought experiment. They are, in the terminology introduced earlier, space-like separated, and for space-like separated events, the earlier discussion established that no absolute fact exists about their temporal ordering precisely because no causal connection between them is even possible. The Andromeda paradox is simply this abstract, previously discussed feature of spacetime geometry, made vivid and concrete by applying it to a specific dramatic case where the distance involved is large enough that the resulting disagreement about simultaneity, ordinarily far too small to notice at human scales, becomes numerically substantial, not microseconds or nanoseconds, but days. Once this distinction is properly understood, the deeper philosophical weight of the thought experiment becomes clear, and it returns directly to the central question animating this entire investigation. If a difference as small as an ordinary walking pace is enough to shift which events on a distant galaxy count as simultaneous with the present moment by several days, then the entire concept of a single, objectively privileged now, applicable across the whole universe, cannot be sustained as a coherent physical idea. There is no way to declare that the stationary observer's plane of simultaneity is the correct one, and the walking observer's plane is somehow mistaken or illusory. Both planes of simultaneity are equally valid, equally well grounded in the mathematics of special relativity, differing only because the two observers happen to be moving at different velocities relative to each other and relative to Andromeda. Neither observer possesses privileged access to some deeper, truer fact about what is really happening on Andromeda right now, because no such fact exists independent of a chosen frame of reference. The very question, phrased as though it demands a single universal answer, turns out to be built on a false premise, one inherited from centuries of Newtonian assumption about the existence of a shared, absolute present moment stretching uniformly across the entire cosmos. This is where the Andromeda paradox does its most important philosophical work, because it forces a confrontation with a question that the earlier, more abstract discussion of relative simultaneity could perhaps be set aside as a technical curiosity relevant mainly to particle accelerators and orbiting satellites. Walking is not exotic. It requires no specialized technology, no extreme velocity, nothing beyond the most mundane and universal of human activities. And yet this thoroughly mundane act, according to the confirmed mathematics of special relativity, shifts an observer's plane of simultaneity across several days' worth of events on a distant galaxy. If those events, whatever they may be, are considered part of the present moment for the walking observer, but not yet part of the present moment for the stationary observer standing beside them, in what sense can it be said that those events have not yet happened in any universal, observer-independent sense? They have already happened for one observer, using nothing more exotic than an ordinary change in walking speed to determine this. And if events several days in what the stationary observer would call the future are already included within the walking observer's present moment, then those events, whatever they are, must already exist, already be real, in precisely the same sense that the walking observer's own present moment is real, because relativity draws no principled distinction in reality or existence between one observer's now and another's, only a difference in which specific slice of the four-dimensional block each observer's own plane of simultaneity happens to intersect. This is the argument, first articulated rigorously by Ritt, Dike, and Putnam, and later refined and popularized through Penrose's clearer formulation, that many physicists and philosophers regard as one of the strongest available arguments for eternalism, the position introduced earlier in this investigation, over presentism. If simultaneity is genuinely relative, and if there is no principled way to declare any one observer's plane of simultaneity more correct or more real than any others, then consistency demands treating every event lying on every possible observer's plane of simultaneity as equally real, equally existent, regardless of whether that event lies in what some other observer would call the past, present, or future. Since observers moving at different velocities can have planes of simultaneity that sweep across enormous stretches of what would otherwise be called future events on distant enough objects, the only way to avoid an incoherent picture in which reality itself flickers in and out of existence depending on which direction someone happens to be walking is to accept that all of these events, spanning what would ordinarily be labeled as extending well into the future, are already real, already existing as fixed features of the four-dimensional block, regardless of whether any particular observer's own world line has yet reached the specific point in spacetime corresponding to their own local experience of that moment. Critics of this argument, and there are serious, carefully reasoned objections raised by philosophers who continue to defend presentism or related positions despite the force of the Andromeda paradox, generally focus on questioning whether planes of simultaneity, as defined mathematically within special relativity, should really be treated as carrying this kind of ontological weight in the first place. A plane of simultaneity, these critics note, is fundamentally a mathematical convention, a particular way of organizing spacetime coordinates that proves useful for certain calculations, but which need not be interpreted as making a direct metaphysical claim about which events are truly real, as opposed to which events are merely calculable using a particular coordinate system. Under this view, the fact that different observers construct different planes of simultaneity says something important and true about the mathematics of relativity, and about the limits of what can be meaningfully compared across observers in relative motion, without necessarily forcing the further conclusion that every event on every possible plane of simultaneity must therefore be equally real in some deeper observer-independent sense. This objection remains a live and active area of philosophical debate, one without a fully settled resolution even among physicists and philosophers who agree completely on the underlying mathematics of special relativity itself. What the Andromeda paradox demonstrates beyond dispute, regardless of where one ultimately lands on this deeper philosophical question, is that the physics itself offers no principled way to privilege any single moment as uniquely, objectively now across the universe as a whole. This alone is enough to place enormous strain on presentism as traditionally understood, the view that only the present moment is real, since presentism seems to require exactly the kind of universal observer-independent now that special relativity's confirmed mathematics shows does not exist. Whether this strain is fatal to presentism entirely, or whether more sophisticated versions of the position can be constructed to accommodate the relativity of simultaneity without collapsing into full eternalism, is a question that has occupied philosophers of physics for decades, and it is a question this investigation will examine directly, weighing the strongest arguments on each side before turning to consider whether some third position, one that attempts to preserve elements of both views, might offer a more satisfying resolution to a debate that the simple, ordinary act of walking has shown to be considerably more consequential than it first appears. Presentism, at its core, makes a claim that feels less like a scientific hypothesis and more like a basic description of how existence works. Only the present moment is real. The past has ceased to exist, persisting merely as memory, record, and consequence. The future has not yet come into being, remaining genuinely open, undetermined, and in some sense not yet part of reality at all. This view is built so deeply into ordinary language and ordinary experience that stating it explicitly can feel almost redundant, like spelling out that solid objects cannot pass through one another. Every tense in every human language encodes some version of this assumption. We say that Rome fell, using a past tense that implies the fall is no longer happening, no longer occurring, existing now only as a historical fact rather than an ongoing event. We say that tomorrow will arrive, using a future tense that implies tomorrow does not yet exist in any meaningful sense, remaining instead a mere possibility until the moment it becomes present. Presentism is not a philosophical position that most people consciously adopt after careful deliberation. It is closer to a default setting, inherited from the structure of perception and language alike, rarely examined because it rarely needs to be. The previous sections of this investigation, however, have assembled a body of evidence that places presentism under genuine strain that comes not from philosophical speculation, but from experimentally confirmed physics. The relativity of simultaneity, established through the Lorentz transformations and confirmed through decades of experiments involving atomic clocks, particle decay rates, and satellite navigation systems, demonstrates that there is no universal observer-independent fact about which events across the universe are happening right now. The Andromeda paradox sharpens this demonstration into something vivid and almost uncomfortable, showing that an ordinary walking pace is sufficient to shift an observer's plane of simultaneity across several days' worth of events on a distant galaxy. If presentism requires a single, privileged present moment shared identically by every observer throughout the universe, then the physics appears to offer no candidate for what that moment could possibly be, since every attempt to define it depends on an arbitrary choice of reference frame, with different frames yielding genuinely different, equally valid answers. Philosophers who continue to defend presentism, and there are serious, technically sophisticated defenders who have not simply ignored this challenge, tend to pursue one of several strategies in response. The first strategy involves questioning whether the block universe interpretation of relativity is really forced upon us by the mathematics, or whether it represents one possible interpretation among several, chosen partly for reasons of mathematical convenience rather than strict logical necessity. This line of argument notes correctly that special and general relativity are formal mathematical theories, describing relationships between measurable quantities like distance, duration, and velocity, without necessarily making direct metaphysical claims about which of these quantities corresponds to something genuinely, fundamentally real, as opposed to something that is simply useful for making accurate predictions. Under this view, the fact that different observers construct different planes of simultaneity is a fact about the mathematics of coordinate systems, and interpreting it as a claim about the ontological status of past, present, and future events involves an additional philosophical step, one that goes beyond what the physics itself strictly requires. This objection carries real weight and deserves to be taken seriously rather than dismissed. Physics, throughout its history, has often produced mathematical formalisms that admit multiple interpretations, with working scientists using the mathematics productively for decades, while genuine disagreement persists about what that mathematics actually implies about the underlying nature of reality. Quantum mechanics offers the most famous example of this pattern, a theory whose predictive success is beyond serious dispute, while its interpretation, what the mathematics actually says about the nature of measurement, observation, and physical reality, remains a matter of ongoing debate among physicists and philosophers, a debate this investigation will examine directly in a later section. It is not obviously unreasonable to suggest that relativity might occupy a similar position, offering an extraordinarily well-confirmed mathematical description of how measurements of space and time relate to one another across different observers, without thereby settling, once and for all, the deeper metaphysical question of whether past and future events are genuinely equally real alongside the present. And yet this objection, however reasonable in principle, runs into a specific difficulty when applied to presentism in particular, a difficulty that many philosophers of physics regard as more serious than the general point about interpretation suggests. The difficulty is this: presentism does not merely claim that the present moment holds some kind of special metaphysical status. It requires that there be a single, determinate fact about which events across the entire universe constitute the present moment, a fact that must exist independently of any particular observer's frame of reference, precisely because presentism claims to describe an objective feature of reality itself, not merely a feature of how some particular observer happens to be measuring things. This is where the relativity of simultaneity creates a problem that goes beyond simple interpretive flexibility. It is not merely that different observers use different coordinate systems to describe the same underlying reality. The way a person facing north and a person facing east might use different coordinates to describe the same physical location without any genuine disagreement about where that location actually is. The relativity of simultaneity involves genuine disagreement about which events occur at the same time, a disagreement that cannot be resolved by translating between coordinate systems because the disagreement is not an artifact of the coordinate system chosen. It reflects an actual, physically measurable difference in how time itself elapses for observers in relative motion, confirmed directly through the kinds of clock experiments examined earlier in this investigation. A second strategy pursued by presentists involves attempting to identify some privileged reference frame, some observer or coordinate system that could be designated as defining the true, objective present moment, even if other frames produce different, merely apparent versions of simultaneity that do not carry the same metaphysical weight. One candidate sometimes proposed for this role involves the cosmic microwave background radiation, the faint, nearly uniform glow of radiation left over from the early universe, detectable in every direction across the sky. Because this radiation fills the universe almost uniformly, it is possible to define a frame of reference in which the radiation appears equally bright in every direction, a frame sometimes called the cosmic rest frame. An observer at rest relative to this frame would, in principle, occupy a privileged position from which to define a preferred cosmic time, potentially offering exactly the kind of universal present moment that presentism requires. This proposal, while creative, faces serious objections of its own. The cosmic microwave background provides a convenient, empirically measurable way of identifying a particular reference frame, but nothing in the mathematics of relativity itself singles out this frame as more fundamentally real or more metaphysically privileged than any other. Special relativity's first postulate explicitly states that the laws of physics are identical for all observers moving at constant velocity relative to one another, with no frame of reference granted special status purely on physical grounds. The cosmic rest frame is observationally convenient, useful for cosmologists studying the large-scale structure and history of the universe, but designating it as metaphysically privileged, as defining the one true present moment against which all other, merely apparent presence must be measured, would require additional justification beyond simple observational convenience. Justification that most physicists working within the standard framework of relativity have not found compelling. It would also sit uneasily with general relativity, which extends the relativity of motion even further than special relativity, incorporating gravity and acceleration into the same framework and making the identification of any single universal frame considerably more complicated. Once curved spacetime, examined later in this investigation, enters the picture. A third, and perhaps more philosophically careful strategy, involves distinguishing between different versions of presentism, some more vulnerable to the relativity of simultaneity than others. A strict global presentism, insisting on a single universal present moment applicable identically across the entire universe, faces the full force of the objections already discussed. But some philosophers have proposed more localized versions, in which presentness is understood relative to a particular observer or a particular region of spacetime, without requiring a single, universally shared present moment stretching across cosmic distances. Under this kind of relativized presentism, it might be coherent to say that only the events on a given observer's own plane of simultaneity are real, from that observer's own perspective, without requiring that this same set of events be considered the uniquely real set from the perspective of every other observer as well. This move preserves something of the spirit of presentism, the idea that reality is tied to a particular now rather than spread uniformly across all of time, while abandoning the specifically global, universal claim that creates the most direct conflict with relativity's confirmed mathematics. Critics of this relativized version of presentism raise a different objection, one that returns to the Andromeda paradox and pushes its logic further. If reality itself is relativized to each observer's own plane of simultaneity, then it seems to follow that different observers, moving at different velocities, inhabit genuinely different realities, with different sets of events counting as real for each of them, and no principled way to combine these different realities into a single, coherent, shared universe. This consequence strikes many philosophers as considerably more radical and considerably harder to accept than the eternalist alternative it was meant to avoid. Eternalism, after all, offers a single unified observer-independent structure, the four-dimensional block, within which every event has a fixed and definite location, even though different observers slice through that block differently when constructing their own local sense of past, present, and future. Relativized presentism, by contrast, seems to fragment reality itself into as many separate, only partially overlapping versions as there are possible observers and possible states of motion, a picture that many find considerably less parsimonious and considerably more metaphysically strange than simply accepting that all of space-time, past and future alike, is equally real. None of this settles the debate definitively, and careful philosophers of physics continue to defend sophisticated versions of presentism and related intermediate positions against the arguments assembled here. What can be said with confidence, resting directly on experimentally confirmed physics rather than philosophical speculation alone, is that any version of presentism compatible with relativity must abandon the simple, intuitive picture inherited from Newton and from ordinary language, the picture of a single, universal now sweeping uniformly across the entire cosmos, illuminating each moment in turn before plunging it into the past. That picture, however deeply embedded in habit and language, does not survive contact with the mathematics of relative simultaneity. Whatever presentism survives this confrontation, if any version does, must be considerably more sophisticated, more qualified, and more carefully hedged than the presentism most people carry unreflectively into their everyday understanding of time. Having examined presentism's difficulties in detail, the investigation now turns to eternalism itself, laying out its positive case with the same rigor, before considering whether either position, taken to its logical extreme, adequately captures what the full range of relativistic evidence actually suggests about the nature of time. Eternalism begins from a simple observation already established through the preceding sections of this investigation. If relativity denies any principled way to designate a single universally privileged present moment, and if the mathematics instead treats every moment as occupying a fixed location within a single four-dimensional structure, then the most direct and economical reading of the physics is to accept all of these moments, past, present, and future, alike, as equally real. This is not a leap beyond what the evidence supports. It is, many physicists and philosophers argue, simply what the evidence most directly implies, once the temptation to smuggle back in a privileged present through some version of the strategies examined in the previous section has been set aside. The positive case for eternalism rests on an argument sometimes called the rigidity of the past, extended by relativity into a rigidity that applies to the future as well. Consider first why almost no one, including committed presentists, doubts that the past is real in some meaningful sense, even though it is no longer present. The past leaves traces. It is recorded in memory, in written history, in the physical structure of the world itself, from geological strata to the light still arriving from stars that emitted it millions of years ago. More importantly, the past is fixed. Nothing that happens now can alter what occurred yesterday. This fixity is often taken as evidence that the past possesses a kind of reality distinct from the openness attributed to the future. A reality presentists typically try to accommodate by saying the past was real, existing now only as memory and consequence, while the present alone is actually real in the fullest sense. Eternalism asks a pointed question of this position. What, precisely, is doing the work of making the past fixed and determinate if the past itself no longer exists? If presentism is correct, and only the present moment is real, then statements about the past, that Rome fell, that the Second World War ended, that a particular person was born on a particular day, must be made true by something other than the past events themselves, since those events, under presentism, no longer exist in any sense capable of grounding the truth of statements about them. Philosophers call this the grounding problem, and it has proven to be one of the most persistent difficulties facing presentism as a coherent metaphysical position. If nothing exists except the present, what makes it true right now that dinosaurs once existed, given that no dinosaur, no trace of a dinosaur beyond fossils, and no direct evidence of the past moment in which dinosaurs were alive, exists as part of the present moment itself? Presentists have proposed various solutions, appealing to presently existing traces, records, and causal consequences as sufficient grounds for truths about the past. But each proposed solution faces further objections, particularly regarding events that left no trace whatsoever, truths about the past that seem to hold regardless of whether any present evidence happens to survive to confirm them. Eternalism dissolves this problem entirely by refusing to treat the past as ontologically different from the present in the first place. Under eternalism, statements about the past are made true by the past events themselves, existing as fixed, definite regions of the four-dimensional block, just as real and just as capable of grounding truth as any event occurring in what a particular observer happens to call the present. This is not a minor technical convenience. It resolves a genuine philosophical difficulty that has troubled presentism for as long as the position has been seriously examined, and it does so simply by extending consistently an intuition almost everyone already holds about the fixity and reality of the past, applying that same intuition to the future as well, since relativity gives no principled reason to treat the two temporal directions asymmetrically once a single universal present moment has been abandoned. This brings the discussion to what many consider the strongest and most direct argument for eternalism, one built entirely from physics already established in this investigation, rather than from purely philosophical considerations about grounding and truth. If the relativity of simultaneity is correct, and it has been confirmed through the atomic clock experiments, the muon decay measurements, and the continuously functioning correction systems built into GPS satellites, then for any given event occurring on Earth, there exist other observers elsewhere in the universe, moving at different velocities, for whom events lying in what we would call our future are already included within their own present moment. The Andromeda paradox demonstrated this using nothing more exotic than an ordinary walking pace and a sufficiently distant galaxy. If those future events, real for another observer's present moment, are genuinely real for that observer, and if there is no principled physical basis for declaring one observer's present more authoritative than another's, then those events must already be real in an observer-independent sense as well, since their reality cannot coherently depend on which particular observer happens to be doing the labeling. This argument, first developed rigorously by Reitdijk and Putnam and refined through subsequent discussion, proceeds through a small number of individually plausible steps that combine into a conclusion many find difficult to resist once each step is granted. If an event is real for some observer's present moment, it is real, full stop, not merely real relative to that observer in some watered-down, merely perspectival sense, since presentism itself insists that present events possess a robust, non-relative kind of reality, exactly the kind of reality eternalism argues cannot coherently be restricted to a single observer's frame once relativity is taken seriously. If some observer's present includes events that another observer would classify as future, and those events are real for the first observer, they must be real. Period. Since reality does not come in observer-relative varieties without collapsing into the fragmented, difficult-to-sustain picture discussed in the previous section. And since this reasoning can be applied to any event anywhere in the universe, using an appropriately chosen observer moving at an appropriate velocity, it follows that every event throughout the entire history of the universe, past and future alike, must already be real, existing as a fixed feature of a single four-dimensional structure rather than coming into being progressively as some universal present moment sweeps forward through time. It is worth pairing this philosophical argument with the specific physical facts that make it more than a merely abstract exercise in logic. The events reachable through this kind of reasoning are not confined to some narrow, negligible window close to the present moment, because the tilt in an observer's plane of simultaneity grows in proportion to both the observer's velocity and the distance to the events in question. Sufficiently distant events, combined with sufficiently high, though entirely achievable, relative velocities, can bring events years, decades, or in principle, far longer stretches of what would ordinarily be called the future within reach of some observer's present moment. There is no theoretical limit built into the mathematics of special relativity that confines this effect to a narrow band close to whatever we currently designate as now. The only limiting factor is the combination of distance and relative velocity required, both of which can, in principle, be made arbitrarily large, extending the reach of this argument correspondingly far into what would otherwise be called the future. This does not mean that a person walking down a street possesses any special access to future events, in any sense that could be exploited to gain information not otherwise available. The argument from the Andromeda paradox never suggested that observers gain knowledge, still less that they could act on such knowledge based on shifts in their own plane of simultaneity. It is important to distinguish carefully between the metaphysical claim that certain future events are already real, part of the fixed structure of the four-dimensional block, and the epistemological claim that observers can somehow access or exploit this fact. These are entirely separate questions. Eternalism, as defended through the Reitdijk-Putnam argument, makes only the first claim. It says nothing about whether or how information about future events could ever become accessible to an observer in the present, a question that touches on entirely separate physical constraints involving causality, information transfer, and the light cone structure examined earlier in this investigation, constraints that remain fully intact regardless of whether eternalism or presentism turns out to be the correct picture of time's underlying nature. Beyond the specifically relativistic arguments, eternalism draws additional support from a broader consideration, sometimes called the parity argument, an argument that predates relativity but gains considerable additional force once relativity's confirmed mathematics is brought to bear on it. The parity argument notes that space and time prior to relativity were already suspected by some philosophers, including Leibniz in his correspondence with Clarke discussed earlier, to be more similar in structure than ordinary intuition suggests. No one considers a distant location in space to be less real simply because they are not currently standing there. The city of Lisbon does not depend for its continued existence on someone currently occupying it, observing it, or standing within its boundaries. It exists, real and complete, regardless of any particular observer's current location, and the same is true of every other place in the universe, occupied or unoccupied, observed or unobserved. If time is genuinely comparable to space, woven together with it into a single four-dimensional structure, as Minkowski's mathematics demonstrates, then consistency seems to demand extending the same reasoning to temporal locations as well. A moment in 1850 does not depend for its reality on any observer's consciousness currently occupying that particular slice of space-time, any more than Lisbon depends on someone currently standing within its city limits. Critics of the parity argument, and there are thoughtful critics who accept the relativistic evidence while resisting this particular extension of it, point out that the analogy between space and time, however illuminating for understanding the mathematics of relativity, may nonetheless break down at a deeper metaphysical level, one not fully captured by the geometric formalism alone. Time, these critics note, possesses features that space simply does not, most notably the felt experience of passage, the seemingly undeniable sensation of moving from one moment to the next, a sensation with no clear spatial equivalent. No one experiences themselves as moving through space in quite the same involuntary, continuous, and universally shared way that everyone experiences themselves as moving through time, aging, remembering, anticipating, in a manner that appears to demand some kind of explanation beyond simply pointing to the geometric similarity between spatial and temporal dimensions within Minkowski's formalism. This objection reintroduces, in a more careful and precise form, the very question that opened this investigation. If the block universe is correct, if all of space-time is a fixed, unchanging four-dimensional structure with no genuine flow built into its geometry, why does experience so insistently, so universally, and so consistently present itself otherwise? Addressing this question adequately requires moving beyond the geometry of space-time itself and into the physical processes that might explain why conscious experience, embedded within an unchanging block, would nonetheless generate the persistent and near-universal impression of time flowing steadily and irreversibly in one particular direction, an impression that the next stage of this investigation traces back not to the fixed structure of space-time, but to a quantity that does appear to change consistently throughout the universe, the steady, measurable increase of disorder itself. A third position exists between presentism and eternalism, one that attempts to honor the intuitions supporting each while avoiding what its proponents see as the most troubling consequences of both. Developed most rigorously by the philosopher C.D. Brought in the early 20th century, the growing block universe proposes that the past and the present are both fully real, existing as fixed, determinate regions of spacetime, while the future remains genuinely open, not yet part of reality in any sense at all. Under this view, the universe resembles a book being written one page at a time. The pages already written are permanent, unalterable, and just as real as the page currently being composed. But the pages not yet written do not exist in any form whatsoever, not even as an undetermined possibility waiting to be filled in. They are simply and completely absent from the story so far. The appeal of this position becomes clear once its motivations are examined directly. Presentism, as the previous sections demonstrated, struggles with the grounding problem, the difficulty of explaining what makes statements about the past true, if the past itself no longer exists in any sense. The growing block universe solves this difficulty immediately and directly, in exactly the same way eternalism does, by insisting that past events remain fully real, fixed permanently within the block, available to ground the truth of any statement made about them regardless of how much time has since elapsed. A dinosaur that lived 70 million years ago is not, on this view, reduced to a mere memory or trace. It occupies a real, determinate region of space-time, as real as anything happening today, differing from the present only in its position along the growing structure rather than in its ontological status. At the same time, the growing block universe attempts to preserve something eternalism appears to abandon entirely, a meaningful distinction between the fixed, settled past and the open, undetermined future. This distinction matters enormously to a great many philosophers and to a great many ordinary intuitions about the nature of choice, possibility, and human agency. Under strict eternalism, as laid out in the previous section, Every event throughout the entire history of the universe, including every event that has not yet occurred from any given observer's perspective, already exists as a fixed feature of the four-dimensional block. This raises an uncomfortable question that this investigation will examine in considerably more depth later, when the topic of free will is addressed directly. If your entire life, from birth to death, already exists as a complete, unchanging world line within the block, in what sense can any of your future choices be said to be genuinely open rather than simply not yet experienced by you, despite already being fully determined and fixed in every detail? The growing block universe offers what looks at first glance like an elegant solution to this discomfort. The future, on this view, is not merely unexperienced. It does not exist yet, in any sense, which means it remains genuinely open, unwritten, available to be shaped by choices, chance, and physical processes that have not yet occurred and whose outcomes are not yet fixed by anything in the standing structure of reality. This is an attractive picture, and it is worth appreciating why serious physicists and philosophers have continued to take it seriously, despite the difficulties it runs into once relativity is brought fully to bear on it. Those difficulties, however, turn out to be substantial, and in certain respects, they mirror almost exactly the problems that undermined presentism in the earlier discussion of relative simultaneity. The growing block universe requires something that presentism also required: an objective, universal boundary, a definite edge separating the real, already written past and present from the unreal, not yet written future. Broad, writing decades before the full philosophical implications of relativity had been widely absorbed outside physics itself, imagined this boundary as a kind of advancing front, sweeping forward through the universe, converting successive moments from unreal potential into real, fixed actuality as it passed. This advancing front plays precisely the same conceptual role that the universal now played in classical presentism: a single, objective, observer-independent marker dividing reality from non-reality across the entire cosmos simultaneously. And this is exactly where the relativity of simultaneity reasserts itself as a serious obstacle. If there is no principled, physically meaningful way to define a single set of events occurring simultaneously across the universe, as the Andromeda paradox demonstrated so vividly using nothing more than an ordinary walking pace, then there is equally no principled way to define a single advancing edge separating the real from the not yet real. Whose plane of simultaneity determines the location of the edge? The observer standing still or the observer walking past them, whose own calculation places several additional days' worth of Andromeda's history on the already real side of the boundary? Both observers, according to the confirmed mathematics of special relativity, are equally correct within their own frames of reference, which means the growing block universe faces the identical difficulty that proved so damaging to global presentism. There is no experimentally or theoretically privileged frame available within special relativity to designate one particular slicing of spacetime as the true objective edge of becoming, as opposed to any of the countless other equally valid slicings available to differently moving observers. Some philosophers have attempted to rescue the growing block model by redefining the advancing edge not as a flat plane of simultaneity, the kind that generates the relativity problems just described, but as something more closely tied to the light cone structure examined earlier in this investigation. Under this modification, an event becomes real, joins the growing block, once it lies within the past light cone of some sufficiently advanced point in the universe's development, a definition that uses only the observer-independent, absolute structure of causality rather than the frame-dependent structure of simultaneity. This approach avoids some of the most direct relativity-based objections, since light cones, unlike planes of simultaneity, are genuinely fixed features of space-time geometry that every observer agrees on regardless of their own motion. But it introduces new complications of its own, particularly when applied across the vast causally disconnected regions of the universe that current cosmological models suggest exist, regions separated by distances so great that no light cone from any single point could plausibly encompass the entire universe's worth of simultaneous becoming that the growing block model seems to require. A separate and quite different objection to the growing block universe emerges not from physics directly, but from a careful examination of what the model implies about knowledge and experience, an objection developed prominently by the philosopher David Braddon Mitchell. If the growing block universe is correct, then at any given moment, the vast majority of moments that have ever existed or will ever exist throughout the entire history of the universe lie in the fixed, already written past, with only a vanishingly thin, momentary edge representing the genuinely new, freshly created present. Given this overwhelming numerical imbalance, an observer, waking up at some arbitrary point and asking what time it is, subjectively, should expect on purely statistical grounds to find themselves located deep within the fixed past, among the overwhelming majority of already written moments, rather than at the exceedingly thin, statistically unlikely edge of becoming. And yet every observer, without exception, experiences themselves as located precisely at the growing edge, at the present moment, never at some fixed point safely nestled within the already completed past. This mismatch between what the growing block model would statistically predict about where observers should find themselves and what every observer actually experiences without exception poses a genuine epistemic puzzle, one that proponents of the growing block universe have not yet fully resolved to the satisfaction of most critics. Taken together, these difficulties have led many physicists and philosophers of physics to conclude that the growing block universe, whatever its intuitive appeal in preserving a meaningful distinction between fixed past and open future, does not sit comfortably alongside the confirmed mathematics of special relativity in the way that full eternalism does. Eternalism requires no privileged edge, no universal boundary of becoming, no objective fact about which events count as already real as opposed to not yet real. It simply accepts the entire four-dimensional structure, past and future alike, as a single, unified, unchanging whole, sidestepping the relativity problems that trouble both presentism and its growing block cousin precisely because it declines to draw any objective, frame-independent line through spacetime in the first place. This does not mean the growing block universe has been definitively refuted, and serious, technically careful work continues to explore ways the model might be reconciled more fully with relativistic physics. But it does mean that, among the three major positions examined in this investigation, eternalism remains the one most directly and most comfortably supported by the specific experimental evidence already assembled, from the atomic clock experiments to the Andromeda paradox. None of this, however, resolves the deeper puzzle that has been quietly accumulating throughout this entire discussion, the puzzle first raised at the very beginning of this investigation and repeatedly deferred. If eternalism is correct, if the entire four-dimensional block already exists complete and unchanging, with no genuine flow built into its underlying geometry, why does conscious experience so insistently, so universally, and so consistently present itself otherwise? Why does every observer, without exception, experience time as moving, as passing, as flowing, steadily in one direction, from a fixed and unchangeable past toward an open and uncertain future, when the physics itself contains no equation, no structural feature that distinguishes one temporal direction from the other? The answer, it turns out, does not lie in the geometry of spacetime at all, but in a separate physical quantity, one that does genuinely and measurably change throughout the observable universe, increasing steadily and, as far as every confirmed observation to date can determine, irreversibly, the quantity known to physicists as entropy.